You know these AI models like chatgpt, right? They can feel like total black boxes, pure magic. But have you ever wondered what's actually going on under the hood? Well, today we're going to pull back that curtain. We're going on a journey to see how a large language model is built, starting with the most basic ideas and going all the way up to the principles that power the most advanced AI today. All right, let's get into it.
It really all comes down to this one big question. How do you take a machine which only gets ones and zeros and teach it to produce text that actually feels human? The secret isn't teaching it to understand things the way we do. It's about getting it to master one very specific and very, very powerful task.
So here's the game plan for our explainer. First up, we'll look at the absolute core task of it all, just predicting the next word. Then we'll explore the attention mechanism. That was the breakthrough that basically gave these models a long-term memory. From there, we'll check out the transformer architecture that attention made possible. After that, we got to talk about the insane amounts of data and hardware required, and we'll wrap up with the scaling laws, which kind of revealed a surprising truth about how to make these models better.
All right, let's kick things off with Section 1, the core task. And it sounds simple, but this idea is at the heart of literally everything else we're going to talk about. All the incredible abilities, all the mind-bending complexity of these models, it all grows from this one single goal.
That's it. That's the entire game. At its core, an LLM is a next word predictor. Think of it like a super-powered autocomplete on your phone. It's been shown a gigantic library of text, and its only job is to look at a string of words and guess, with the highest probability, what the very next word should be. It just does that over and over and over again to build sentences, paragraphs, and even entire essays.
Okay, so how do you make sure the model's actually learning patterns and not just memorizing everything it's seen? Well, you split up the data. Think of it like this. You're studying for a huge exam. You spend most of your time, say 90%, on the course material, learning all the concepts. That's the training data. But then, the final exam is that other 10%, with questions you've never seen before. That's the validation data. This test is crucial because it proves the model can apply what it learned to new situations, which is exactly what you want.
So that foundation is key, but it leads to a really big problem. Just predicting the next word based on the last word you saw, that's not nearly enough. Language needs context. And that brings us to our second section, the attention breakthrough. This is what solved a massive memory problem that held back older models.
I mean, think about it. To understand a story, you need to remember who the characters are and what happened in Chapter 1. Early models, like something called a Bigram model, could only remember the one or two words that came right before. It's like trying to read a novel by looking through a tiny little pinhole. You have no idea what the bigger picture is. And for a long time, this was the wall that AI researchers had hit. And then, in 2017, this happened. A team of researchers at Google published this paper with a bold, almost cocky title, "Attention is all you need." And honestly, they were right. This wasn't just a small update, it was a seismic shift that basically unlocked everything that was to come.
So what was this revolutionary idea? It's a mechanism called self-attention. And here's what it does. Instead of just looking at the word that came right before, self-attention lets the model look at every other word in the sentence, or even the whole document, and decide which of those words are most important for understanding the current word. It learns relationships, it learns dependencies, no matter how far apart those words are. It learns context.
This is the perfect way to see how it works. Take the word server. In that first sentence, the model learns that server should pay a lot of attention to the word crashed. That connection instantly tells it, aha, we're talking about a computer. But in the second sentence, server pays attention to the word check. And boom, the context completely flips. The model knows we're talking about a person in a restaurant. Same word, totally different meanings, unlocked by context. That's the power of attention.
Now, this amazing breakthrough wasn't just an idea floating in the air. It became the heart of a brand new architecture. And that brings us to Section 3, the transformer blueprint. This is the design that powers pretty much every major LLM you've heard of today.
Okay, I know, this looks like a lot of jargon, but think of it like this. A transformer is built by stacking these basic blocks, like Legos, one on top of the other. The star player, the one we just talked about, is multi-head self-attention. That's the part that figures out the context. Then you have things like feed-forward networks that do the heavy lifting, the actual computation. The other parts are basically clever plumbing. They just make sure the information can flow smoothly through dozens or even hundreds of these layers without getting all jumbled up.
But of course, this incredible power came with a catch. The original version of self-attention had a major bottleneck. Its cost, in terms of computer power, grows quadratically. So put simply, if you double the length of the text you're processing, the amount of work the computer has to do doesn't just double, it quadruples.
This relationship makes processing really long documents incredibly slow and expensive, and it's why there's a whole field of research today dedicated to finding more efficient transformers.
So now we've got the blueprint. What do we need to actually build the thing? Well, that leads us to Section 4, data, hardware, and training. You can think of these as the fuel and the massive engines you need to bring these models to life. Just to give you a little perspective on the scale we're talking about, the tutorial model we're referencing for this explainer was trained on a dataset that was 45 gigabytes of pure text. Now, that is a ton of information, and it's what's considered the starting point for a teaching model.
Okay, now let's level up. Take a look at the data diet for a real state-of-the-art model like Chinchilla. Suddenly, that 45 gigs looks like a drop in the ocean, right? It's not just one source. It's this carefully balanced mix of text from all over the web. Books, news, code from GitHub, you name it. This incredible variety is what gives the model such a broad understanding of the world.
And you cannot process that much data on a normal computer. Not even close. Training an LLM requires just a staggering number of calculations happening all at once, specifically a type of math called matrix multiplication. And it just so happens that's exactly what GPUs, or graphics processing units, were designed to do. The things that make your video games look so good are also perfect for this. They can do these specific sums way faster than a normal CPU, making them absolutely essential.
So we've got the architecture, we've got the data, we've got the hardware. And for a while, the strategy was pretty straightforward. Just get more of everything. This brings us to our final section, the new rules, scaling laws. This was a discovery that really changed how people thought about building these models.
In the late 2010s, researchers started noticing something kind of incredible. As this quote says, they found that when they made their models bigger and fed them more data, their performance just kept getting better. And not just better, but better in a predictable, straight line on a special kind of graph. It seemed like there was no ceiling. This idea became known as the scaling laws hypothesis.
But then, the insight got even deeper. It wasn't just about making everything bigger willy-nilly. By running hundreds of experiments, researchers found a kind of golden ratio. These squiggly lines you see here from that famous Chinchilla paper proved it. For any fixed amount of computing power you have, there is a perfect, optimal balance between how big your model should be and how much data you should train it on.
And this slide is the ultimate proof. Gopher was an absolute monster of a model, 280 billion parameters. Chinchilla was much smaller, at only 70 billion. But, and this is the key, it was trained on 4 times more data. Because it hit that optimal ratio dictated by the scaling laws, the smaller Chinchilla model actually beat its giant predecessor on almost every test. It showed that the real secret isn't just size, it's the balance.
Which leaves us with this final thought. We've gone from a simple next word predictor to an architecture that can actually understand context, and now to a set of scientific laws that tell us the best way to build them. So as we get even better at finding that perfect balance between the model and its data, what new emergent abilities are just waiting to be unlocked?